Hunter, are you ready?
Yes.
Where's Hunter?
We switched. I
Well, you better hope he comes or you're going to be absent. You.
No, I'm Hunter.
Took a little help to figure that out, did it? All right. Hey.
Afternoon.
Good morning.
Morning.
All right, I have been asked, can I solve this? And I thought he meant, would I solve it for him? Hunter, bring all your stuff and come up here. Just practicing.
I'll catch you. I'm ready.
And I said, no, I can't solve that for you. And I walked away mumbling, I didn't figure he could. I can't solve it, and he can't either. Well, not quite true. I just thought since it was statics, it wouldn't be that bad. It wouldn't be that hard. I don't know how to pronounce that name. Oh, that's the guy behind him. Green?
Yes, sir.
You're going to be sitting up here next to Hunter in a minute. All right. Here's a problem with a beam with 3 supports, and it's got a pin in it. Now, I'm not going to sit here and solve the whole thing. You should be able to do the solution. Let's just say you were asked for the bending moment at C, and we'll just say C is right there in the middle. It's your job to take a unit load and roll it across the structure and solve for the moment at C at each of the points, and whatever you get for the moment at C, plot the resulting answer where the load is applied. So I've got a unit load. I'm going to go ahead and break it up into 2 structures. There'll be a shear passing through this point. There'll be no moment passing through that point, so I've only shown you shear. If there was a moment, I'd stick a moment on there too, but you know, it can't be statically indeterminate yet. We'll get to those later. The distance is 5 feet, 10 feet, 5 feet, 20 feet. First, I put the unit load out here on the end. 5 times 1 has to be balanced by this shear times 10. And so this would be a half of a kip of shear. And I'm going to show them the way they really go. I'm not going to show them, you know, I've told you that we really ought to be showing these shears and moments inside the beams positive, but for right now I just want to make sure it sits still. If someone is holding this side of this little beam down, then he is pushing up on that little piece of beam. If you sum moments about this point right here, you'll notice a half times 25 has to be balanced by something times 20. And I don't know what that is. I'm just going to put, yes, I know how to do that. Some moments about this point to get 0.5 times 25 to balance this reaction times 20. And then I'll sum forces vertical. Since this is further out, this will be bigger than a half. Who knows, maybe 0.7. And therefore, this is winning in the vertical direction, so this reaction will go up. I'll sum forces vertical, and I have that right there. Then you asked me to draw the influence line for the shear, for the bending moment at C. Then I would cut it at C and multiply that known reaction times 10 feet, and I would plot the resulting answer here on the influence line. Now, I've done these a long time, so I don't mean to say it looks almost trivial, but it looks pretty straightforward. Then you're supposed to move the unit load someplace else, let's say 5 feet over. That one I can do without a calculator. That's a 1. This is a 0. That's a 0. This is a 0. And that's a 0. And therefore, when you cut through at point C to solve for the moment, this guy located here will cause no moment, and I'll plot 0 here. Then I move the load over another 5 feet. That looks like a load in between two supports. If that's a 1, this one would be a 0.5. This one went down, but this one will go up. 0.5 up, therefore 0.5 down. Again, start on this beam here. If this is down, this reaction is up by some moments about this point. 0.5 times 25 minus this times his moment arm of 20. I can do that. Some forces vertical, I can do that. I can now cut it at point C and multiply the reaction that I did times 10, and I plot that number at this location on the influence line. Then I move the unit load to here. That's obviously then going to make this a 1. That's going to make this a 1. That's going to make this a 0, because you some moments about this point to get 0. 1 times 25 minus this times 20. I can get that reaction. Some forces vertical. I can get, that probably goes down. I can get that reaction. Here looks like the bending moment. Actually, this reaction, this is down on this side, so that'll be down on that side. This one was up, so that will be up. Looks like this moment is going to change sign as this unit load goes across. And again, you cut it, and you solve for the moment. Then you move the load a little bit to the right, and you get the numbers. Then you move the load a little bit to the right, and you get the numbers. Now, from now on, these will be 0. And when it's here, in other words, because of this beam right here, if you sum moments about that point, this number has to be 0, or this little piece will swing around. So I don't know who asked. I don't want to embarrass you. It could very well be nobody in here could have done it. But it's really just that easy. I understand that some of you have a medical problem and that your doctor told you that you could cure your insomnia if you would just come to Lowry's class. However, now if you say, I don't want to do it that way, well, I don't care, because you got to do it that way, because I may very well ask you to do it on a quiz. But if you want to see what the answer is before you start, then I can hardly stop you from doing that. Therefore, if you have been asked on this structure to solve for the bending moment at the influence line for the bending moment at C, then you would take this piece of steel home with you, and you would put a 45-degree kink in it. This dimension is 10. This dimension is 10. This dimension is 5. This is 10, and this is 5. If that's 10 and that's a 45-degree down, 45-degree angle, then you bent your beam 10 feet down. And when you bring it back, you'll find one of the pinholes matches nicely, and one of the pinholes is 10 feet off. Therefore, you will raise this number, roll it up. It's going to roll about this reaction right here. Roll that up 10. If this point rolls up 10, this point will roll up also. More or less? Less, because it's not as far out. It's only half as far out, so it only rolls up half as much. If that rolls up 10, this little piece right here rolls up 5. And if that rolled up 5 on a 10-foot rolling radius, then this little piece right here is going to roll down 2.5. And therefore, this little piece will have to still connect with it. And if that's 2.5, then this height right here is 1.125. And there's your influence line. Doo-doo-doo-doo-doo. Just that easy. Statics, though, I'll tell you, sometimes they get so ugly that I can't figure out what they do either. So then I just do what you did here. Just keep moving the little unit load across the thing and find out the answer that you're looking for. Yes, sir.
How do you know where to put that pin?
I didn't, had no idea. I went into work and I didn't know what I was going to do. The boss came and said, I noticed you finally dragged into work here. I said, well, yeah, I had an interview. I might have some good excuse, you know. Yeah, and he says, well, all right, I've already got Sally working on the shear at A and Joe working at the moment at A, and I already got Sam working at the shear at the pin, so I want you to go draw an influence line for the moment at C. It was an assignment. And therefore, he said, find an influence line for the moment at point C. Thank you, Dan. That's why I kinked it at C, because that's what I was told to find. Then I brought it in about 5 o'clock, and everybody else had left, and he says, don't plan on going anywhere yet. You still got to put the wheels on this thing before you go. And I said, oh, man, bummer. I had a big wheel, I had a little wheel, and I had a lane loading, which I had to drive across this thing. And so for maximum positive moment at C, I put the lane loading here, and I put none here, and I put some lane loading here, wherever there was some positive influence line. Then I took the big wheel, and I put it right here, because that's the biggest positive value on the shear, on the influence line for a moment at C. And I put the little wheel next to it, and I multiplied the magnitude of the little wheel times the height of the influence line, plus the magnitude of the little wheel times the height of the influence line wherever he was now sitting. If he was longer than 10 feet, I put the little wheel off the span so it wouldn't get in this negative area. And then I multiplied the height of this lane loading times the area under this triangle, plus the height of this lane loading times the area under this triangle. And I put a box around it, and I went home. So your question's very good. Why did you kink it at C? That's a given. It's like, why did you use a 40-tip wheel load? That's not a question. I mean, somebody got to tell me those numbers, what to do. Yes, this was where this is what the beam used to look like before I took it home. And I took both of those beams home, nice and straight. This hinge right here, yeah, I took the hinge there. I took it home too. I put this part on my truck and it stood out straight. This piece here drug on the concrete all the way home. Then when I got it home, I put it on the curb and I bent a 45-degree shape out of it, and I hauled it back home with me, back to the job with me. And this pin, when I put the pin in, the thing looked like this. And incidentally, this pin went in there nicely. Then I realized, well, I can't do that because if a truck comes across here, there's no support on this end. And I rolled this up so the pin again fit. And I stuck a steel pin in there. As I did that, this kink at A moved up to A prime. This old piece B here moved down to B prime, and this piece right here, C, moved up to C prime. It's really just a geometry problem. But I mean, it's so fast. You see how fast it is. I mean, look at all this junk. You really need to learn how to do it, because otherwise, if you sit there and cut them during a quiz, we're going to be here all night. All right. Now, I could tell I was losing ground on this one. That's why I gave up last time. So I'm going to start over. We're not going to do anything different, but I'm going to say that this is point A, B, C, D, E, and F. Horror of horrors. The guy has asked you for the shear in span BC. I think we did CD last time, and we got a ways through it, so you can go back and finish it. I want to know the shear in span BC for this beam. Sadly, as you run your little unit load across, you're not actually running it across the beam. You're actually running it across these little panels that span between these girders. Now, not that that matters by statics or by Mueller-Breslau. In other words, if you'll do exactly what I just did 10 minutes ago and put your unit load there and solve for the shear in this span BC, you'll get a number. And if you then move the load maybe halfway, then maybe to the left of this and to the right of this in the middle, you'll develop the entire influence line, which will tell me where I need to put the wheels and where I need to put the lane loads to cause the maximum shear in that panel so that I can design the web to do the job. That's a 446 problem when you get there. Now what I'm going to do is I'm going to deform the structure in shear. I'm trying to remember what color I used here, and hopefully this will make it somewhat more clear. Here is the original structure, just like we showed a while ago. This is the guy we're trying to develop the influence line for. If you were asked to develop the influence line for member A, B on top of those things, it would simply be a simply supported beam. You'd ask the boss, where do you want me to get the influence line for shear for your beam AB? And you'd do it just like any of the rest of them. This one's obviously a little uglier. Now I'm going to come in here and take it off of the supports, and I'm going to take it home, and I'm going to deform it. I'm going to kink it in shear. Here's what the structure looks like at my house. I'm not sure that blue will show up or not. I don't know on the notes. It'll come over straight across here. It'll come up here. We'll just call right at the beam 0. We'll come up an inch. That's 1 inch. And then we'll come across, and there is your unit shear kink inside of the structure. It's blue. It's blue. Now then, you find that this pinhole still fits nicely when you bring it back. Forget about all these little beams on the top for right now. But the little pinhole at B, sadly, does not. Well, that B stands for blue, doesn't it? This little pinhole doesn't fit on the reaction. So it's now your job to roll this thing down 0.2, 0.4, 0.6, 0.8, 1.0 till it gets there. Now, I'm trying to remember. That's okay. I'm trying to remember how I drew it so neat before. If you'll agree with me that we're going to roll about this point A, the blue line, and if you'll agree that that point's going to roll down 1.00, then this point right here is going to roll down some amount. This point's going to roll down some amount. This point's going to roll down some amount. This point's going to roll down the whole amount. So what I'm going to do is I'm going to ask you for the blue kinked line, how far does this point right here roll down? I don't have numbers on here. They're obviously all the same dimension. I say that they're 10 feet, 10 feet, 10 feet, 10 feet, 10 feet. How far is this guy who is 10 feet out going to roll down out of the total of 1.0 rolling down at a radius of 50 feet? 0.2 is correct. In other words, this thing is going to roll 1/5 as much as this guy rolls down, or 10 out of 50. So it's going to roll down 0.2, and that's where I got that point from. Let me get that B out of there. Now this point right here used to be kinked at a number 1.0. It's at the same distance out, and I understand, when you see something curved like that, you think it's going to arc over. But this unit deformation, it's just a little tiny thing. I'm just exaggerating it so we can see it. This point was up here 1.0. If the bottom of that vertical stick rolled down 0.2, then this would have to roll down 0.2. So this number right here is 0.2. And where this point right here is now is 0.8, 0.2 lower than 1.0 where it used to be. And this one's going to roll down 0.2, going to roll down 0.4. This one's going to roll down 0.6. This one's going to roll down 0.8, and this one's going to roll down the full 1. And so I'm going to show you another curve. I'll draw it in red. You'll notice those two lines are parallel. And the reason they're parallel is they were parallel before you rolled it, and just because you rolled it as a rigid body, they're still parallel. The only thing you might complain about is you might think that this line here really shouldn't be vertical, but it's not enough to talk about. Now that's what the influence line looks like for the beam. Sadly, you decided not to roll your unit load on the beam. Instead, you rolled it on these little panel points here. And therefore, rather than drawing the final answer, as submitting it to you as the red line, I instead am going to tell you that the final answer is where these little beams went. This first little beam, this first little panel did indeed go from there to there. So I'm going to show you the first little panel. I'm going to put it under it a little bit. Can't hardly fit it on top of it. There's what happened to the little panel. The little panel went down 0.2. The next time I see your beam being touched is right here, which means that this little beam right here went down on the left and it went up to here, which means it went like this. Now you get the same thing from statics. If you just flat can't see that and don't believe it, then when I give you one of these on a quiz, you'll cut the beam and solve for the answer using statics. This number is 0.8. Therefore, this number is 0.6. This number right here is 0.4. This number right here is 0.2. And this number right here is back to 0. Because all I'm doing is, here's your real beam. And all I'm doing is asking you, where did this guy end up and where did this guy end up on the kinked structure? Because the load itself never saw this. The load itself fell on the little top panel. Now your first question might and probably ought to be, I'm not sure that's fair. You cut it slightly to the right of the beam, and you told me that was the answer for the shear anywhere inside of this beam from B to C. Why didn't you cut it just to the left of C instead? Here you go. Here's the same beam. Here's the thing that I took home. When I got it home, I kinked it just to the left of this ABC point C. And the color used for the kinked beam is blue. And therefore, here's what the beam looks like. Just short of that point, I'm going to put a kink in it. A unit kink. Oops, not that way. Thank you. 1, 2, 3, 4, 5. And then it's parallel to the original line. Here's the point about which that thing is going to be pinned and roll. Here's where this pinhole finally has to end up. When I bring it back on the job site, just for the beam, I ask you, how far does this point have to roll down? Your answer is a 1. And then I'll ask you, where did this point on your beam go? Went down 0.4. Okay. 0.2, 0.4. And this point just a little bit to the right is at 1, but if the top of that little stick went down 0.4, then the top went down 0.4, 0.2, 0.4. It gives me a number there, 0.6. And this point here goes back down to 0. So I'll show you where your main real beam went. And if you wouldn't put those stupid little girders on there and put the little panels across the top, we wouldn't have this problem. That would be the shear influence line for your beam. Except, here's this little panel. Let me give you the influence line for that piece of your diagram. Then that beam went to here. That's a 0.2. And this side went to 0.6. You can see it. There it is. It's 0.6 above the line. And then it goes on, and the little panels all go down with the beam. How about that? 0.2 up to 0.6, 0.4, 0.2, 0.2 up to 0.6, 0.4, 0.2. Tells you exactly where to put the wheels. Tells you where to put the uniform lane loading to get the maximum shear in that panel. You're going to have to solve for the location when to stop putting lane loading. That's easy enough. It's in proportion. 0.2 is to x as 0.6 is to 10 minus x. All right. And the one we did the other day, a little more neatly drawn, so I'll post it. We were asked for the shear in the panel between these two girders. And it turned out that here was your unit kink. Roll it down. This was 4/10 of the way over, so it was 4/10 of the rotation. This one went down 4/10 also, which left it at 0.6. And then here was the main beam. Then the green line shows you the influence line. This panel here, the left-hand end actually went down with the beam. And the right-hand end was above. So your influence line looked like that. And here it is. If you say, well, I don't think it's fair, you cut to the left. Why don't you cut to the right, cut to the left? Here it is, cut to the left. That gives you the same answer. 0.4 up to 0.4, 0.4 up to 0.4. Now, I don't think anything but practice will really get you that. All right, influence line. What else could you possibly be asked to solve for an influence line? Well, a truss, because that's my bridge. I'm getting ready to design all the members in it. I've got a lane loading and I've got a wheel loading. And here's the decking on this one. I'm going to put it up at the top, and then it is supported about 10 feet down, and the structure is about 10 feet deep, and the trucks go across here. If the trucks go across the bottom, then I would put my unit loads on the bottom rather than on the top. For those to choke a horse. You can tell this is going to be a long lecture. All right, here's what I'm going to do. First, I'm going to start numbering all this stuff. 1, 2. This is one we did the other day. I'll stick it in with this set. 3, 4, 5. Here it is cut in the next panel. 6 and 7. Here is the structure. Here is the unit load. 1. Here are, I need calculators. Whoever I call, boy, you better be ready to give me an answer. Thank you. Some of them I can do by myself. A unit load at A will cause a unit reaction at B and a zero reaction at J. I have been asked to solve for the influence line. Oh, come on. At member Charlie Edward. In other words, there are 20 people work for this firm, and I was chosen to draw an influence line for the axial force in member CE. Sally's doing this one, Sam's doing that one, Joe's doing that one, Tom's doing that one. That one's mine, CE. So I take the structure that we're all using and I run a unit load across it. Now, the truth is the trucks won't push on these members transversely. What will happen is we will actually put a beam across here between the two sides of the truss and a beam across here, and we will put a little panel thing across there so that the truck, when he gets here, will actually cause a force at E and a force at G, because these things are so thin, so small moment of inertia, they got a pretty good area. But if you put the load right here, you would just bend the member. They're not made for that. So I'm going to put the unit load at A. Here is my reaction. Here's my reaction. To get the answer for the force in member CE, if you don't mind, I will choose this as my free body. Here is your free body, unit load at A, unit reaction at B. Here's my force in CE. Here's my force in CD. Here is my force in Baker Dog. If I'm looking for the force in CE, I like CE, I hate CD and BD. I follow them until they meet at a point. I will sum moments about D is equal to 0 is equal to CE times his moment arm is 10. I'm not going to slow down much here. You should be able to do this all day in your sleep. Plus 1 times 8 minus 1 times 8, because I'm going so fast I may make a mistake. I may make a mistake just to see if you can catch me. All right. What's the question? Now, you're right. Thank you. You use the same sign convention I do. Thank you. And if you say no, well, it's because you're using a different sign convention. I usually use that for statics. So I should have put a minus, and then one of these is plus, and one of them is minus. Right. And so CE is equal to? That's correct. CE is equal to 0. And therefore, I will go to the influence line diagram. Here's the influence line diagram. I'll call that page 8A. And I plot a 0 for the answer. And I plot it right there on top of A, because that's where you put your unit load, even though it caused the force in this member. Next, I'll move the unit load to joint C. I don't know how many of these I'll need. I may need them all now that I think about it. I'll move the unit load. That's page 8. Here's 8A. I'm going to call this guy. Where will I get a final answer? This is the influence line for the force in member CE. All right, 8A, we'll move the unit load over. There'll be a 1. That'll cause a reaction. 1, 2, 3. 1, 2, 3, 4. That'll cause a reaction here of 0.75. And a reaction over here, I don't care. That's not in my free body. I will cut my free body as before, like so. Maybe I'll just do this right here. Work 10 feet, 8 feet. Here's a 1. Here's a 0.75. Here's the force in member CE. Here is the force in member. Which way did I show it before? Down, thank you. Down, Charlie dog, to the right, Baker dog. Looking for the force in member, CE. I like CE, I hate these two. Do the same thing. Sum of the moments about point D is equal to 0 is equal to. The 1 goes through the point. The 0.75 does not. Minus 0.75 times his moment arm is 8 feet. Minus CE times his moment arm, 10 feet. When you can't see it anymore, let me know. And that says that CE is equal to negative. So I try and show them all in tension, just for some consistency. If they come out of minus, it means it's a compressive force, and it should be plotted below the line on the influence line. How much?
I think it's 0.6.
0.6 for the final answers. Thank you. 0.6. Has no units because you put a unit load on there with no magnitude. Therefore, it has 0.6 for the magnitude and no units. And now then I'll go to the influence line and I'll plot negative 0.6. And I don't know what it's going to look like on down the road here, so I don't know if I ought to plot it, a little bit so it'll go, or big because it's going to go. I don't know. So I'll just plot it here. If I have to change it, I will. Next, 8A, 8B. I move the unit load over here. It's a 1. That causes a reaction. 1, 2, 1, 2. This is a 0.5 for the reaction and a 0.5. Here's my free body. The reaction is 0.5. This is CE. This is CD. This is BD. This is 10 feet and 8 feet. I'm looking for the force in member CE. I sum moments about D is equal to 0. Is equal to how much? Maybe you already got an answer. I'll take it. CE is equal to 0.4. Negative. Thank you. All right. So I go plot the answer. I have no idea where. There it is. This is 0.6. This is 0.4. I'm kind of getting the feeling it's going to look like that. Tell you what, rather than do all of them, let's go ahead and stick the load out at K, and if it comes out 0.6, 0.4, 0.2, 0, 0.2, remember I said these things always end up being straight lines? Okay, let's take a shot at that. Save us some time. 8A, 8B. I got 2 page 8s. 8A, 8B. Here we go. 8C. Put the unit load out here is 1. That causes a reaction. Some moments about B. 1 times 1, 2, 3, 4 times 5 panels. Minus this times 4 panels. That must mean this is 5 fourths. So that would be 5 fourths. 5 fourths up on only 1 down means this reaction is going to go down 1/4. When you get home and look at this, you'll you'll see the reactions. Some moments about this point, that's probably better. That's 1 times a panel minus this guy times 1, 2, 3, 4 panels. That's the fourth. Here's our free body. Here's the free body. Here's the load, the reaction. Here is Charlie Edward. Here is Charlie's dog. Here is Baker's dog. This is 10. All right. It goes so fast, I can't keep up with you. Some moments about D, some of the moments about D is equal to 0 is equal to, let me write this one down. 1/4 times his moment arm is 8, positive, minus CE times his moment arm is 10. And so you say the answer for CE is equal to, did you get a plus? Yeah. Well, no, actually,
Oh, yeah, plus.
will be a plus. It probably is a minus on your calculator, you know, because you solved for it. All right, is equal to a positive 0.2. That tells me everything I need to know right there. 0.4, 0.6, 0.4, 0.2, 0, 0.2, and 0. There is the influence line for the force in member CE. Now, if you say, geez, man, you must be kidding. I do this all my life. Pays good. Very few people but you now know how to do it. I haven't shared this with many people. You know, how many of there are you? Maybe 60, and another class, another 60 each semester. And how many people are there on the face of the earth? 1 trillion or so. They all need to get across the river. They'd all like you to put the wheels in the right place to make sure it doesn't fall down. It's a good profession. I mean, you can do it for years. You can get old and crippled. They'll roll you in just to get you to do this stuff for them. All right. Now, without a doubt, you want to know the easy way, and I don't blame you. It makes sense to me, too, that there ought to be an easy way. So, the easy way is to deform the structure in the mode that you're looking for the force. So first I'm going to show you how to do the influence line for the reaction at B, or at A, either one. You do the same thing as you did on all the rest of them. If you want to know the reaction at B, then, well, I guess there is no reaction at A, sorry. Then you simply move that reaction along the way it points, 1. And if you think the reaction goes up, then you ought to move this point up 1. And if you move point B up 1, then the roadway where the trucks drive, moves up 1.0. This point right here is not going to move up and down, and therefore I does not move up and down, and therefore here is your influence line for the reaction at A. And the height of this right here, it's a straight line. This height is to 8, as this height is to 4 times 8, and therefore this comes down below the line 0.25. The reaction at B would be just as obvious. Where to put the lane load to get the positive reaction at B? Between A and I. Where to put the big wheel? At A. Where to put the little wheel? If the little wheel is within this It's 32-foot length, which most, I guess, trucks are. I don't know. Some, I guess, are longer than that. Then I'd put any little wheels I could get on there. If there's only one little wheel, if it's further than 32 feet, I'd move it off the span so it did not detract from my answer. Influence line for the force in member CE. I'm going to assume that you're looking for tension, and therefore what I'm going to do is I'm going to shorten member CE. I'm going to put it in tension. I'm going to shorten it tension-wise a unit amount. That means I'm going to take a 1. Well, let me take it right out of here. I don't care where you take it, to tell you the truth, but I think it'll be more obvious what's going on if you take it right out of there. So what I did is I held it together and I framed it so it wouldn't fall down because I'm getting ready to take this member loose. And I had a welder cut it here and cut it there. And then I had them pull these two pieces together and move this point back 1. That means that this little piece right here rolled about point D. This entire thing right here rolled about point D. If you don't mind, let me hold this down just so I can get my act together here. I'm going to hold this steady. I'm going to roll this point to the left 1. When I did that, forget this for right now, the whole thing rolled about point D and it rolled up in the air like this. Because you shortened this member, and this here I held it down just as a reference, and then the whole truss raised up in the air. Now, you caused the problem. I saw you. I saw you when you shortened that member. I knew you were going to cause me problems, and you did. This pinhole no longer lines up with this pinhole. And my question to you, after 8 years of college, can you tell me how high that point moved up? In other words, if a solid piece of plywood rolled to the left 10 feet from the rolling radius, from the rolling point, and this guy is 24 out here, how high is this? Let me draw you another piece of, well, I think you're right. Let me just show you another piece of plywood. There's a piece of plywood. Here it is bolted down right here. This point right here was found to move to the left 1. And it is out here 8 feet. Here's another knot in the plywood, and that point right out there is out here 20 feet. How far did it move in that direction? 1 is to 8, as question mark is to 20. All right, so since this moved to the left 1, it rolled an angle, theta, is equal to 1 divided by 8. 10, excuse me. Because the opposite is 1 and the adjacent is 10, so it rolled, theta is equal to 1 over 10. Then if that piece of plywood rolled theta is 1 over 10, then this point here rolled 1 over 10 times 8 and 8 and 8. And you got 2.4. And it's not inches, it's a 1. Now you say, I'm not sure I didn't just go cut, and get some answers, because I don't know where we're going. Well, here's where you're going. There's only one thing to learn. kink the structure for what you're looking for. If you're looking for a reaction, move the reaction up 1. If you're looking for a shear, put a unit shear kink. If you're looking for moment, put a unit bending kink. If you're looking for the force inside of a truss member, kink the truss member in tension. In other words, shorten it. Then when you find out that your structure doesn't fit where the pins go again, roll the structure until it goes back on the pins. This pin will roll down 2.4, and this guy right here is going to roll down not 2.4 because he isn't as far out. Point D, right below point C, is going to roll down a shorter amount than this guy rolled down. As a matter of fact, since he's 1/4 of the way out, he's going to roll down 1/4 of 2.4. What's 1/4 of 2.4 rolling down? You remember that number? So do I. There's your 0.6 right there after you put it back on the supports. Now then, once I got that number, I'm pretty much through. The main thing I get out of the kinking the structure, our book doesn't like me, or he doesn't like using this thing to get numbers. But he says it's invaluable to know what the diagram looks like. Here's what the diagram looks like. Your only problem, it doesn't fit. But it does give you the values. But if you can't figure out, since this rolls down, if you can't figure out it moved 2.4, at least knowing that the structure looks like this should give you a big heads up on the thing. Because when this rolls clockwise to get this back on this thing, this piece is going to go down. This has no ability to move up and down in the long run because it's right above this point. And then at least all you'd have to do would be to put the load at one location and find the answer. Then all the rest of them you can get due to geometry. All right, let's say I'm going to solve for the influence line for the force in FH. And rather than cut, if you don't mind, I'm just going to cheat. First, what I'm going to do is I'm going to bring my welder out here, and he's going to cut a unit length of the truss out of there. And I'm going to hold this side of the truss down for nothing more than a reference. It's very much like when you brought your beam back. When you initially brought your beam back, you brought it back and just referenced it like it used to be, and you let the kink cause the problems it was going to cause. Namely, it didn't fit. That's all I'm doing now. As I'm going to arbitrarily hold down the left side, I'm going to cut a unit piece out of here. That's going to roll this entire piece of the structure clockwise. How much it's going to roll it clockwise is the old line used to be here. You now rolled it 1 on the arc over 10 on the length. That's a rolling of this piece of plywood right here. Don't know why I put that like that, to tell you the truth, because the whole thing goes. It's going to roll the right section of the truss about point E. And it's going to roll it 1 out of 10. That means that this point right here is going to roll down 1 out of 10. Right there, and right there, and right there. The one I'm particularly interested in is this one, because that's where your structure is no longer going to fit. And so you have caused a problem, you and your welder. Let's call that delta at J. All right. The delta at J is to the rolling radius to point J as the delta at F, which incidentally you did it and I watched you, it was a 1, is to the rolling radius to point F. Delta sub J is to the rolling radius to J. It's out here 16 feet. This thing here is the same as that one, 16 feet. As your welder deformation is to where your welder was, 10 feet down. That lets this be a piece of plywood. It lets it be a rigid body. It lets it roll about point E because you cut out this little piece down here. I take it back. I take it all back. Did anybody see what I did wrong? I was very zealous. But I think everything I got there is wrong. Well, I don't know if it should be compression or tension or what. But if you cut a piece out of FH, where's it going to roll about? I need a point. That's what I wrote down. I don't think that's what I said when we started. Let me give you a hint. As I looked up there and I changed it. There's what I drew right there. And then a second ago I erased it and I put it through this member here. Look at this piece of plywood. And look at this piece of plywood. And look how between those two pieces of plywood there used to be a little steel bar, which your welder cut a chunk out of. That's exactly what's going to happen, just what you did with your hand. It's going to roll about G. That's correct. So don't ever make that mistake. You'll really look stupid. If you want to know the influence line for this member, you'll cut an inch out of this member, and where will it roll? About F. And if you want to know the force, the influence line for the force in member GI, then you'll cut an inch out of GI, and it will roll about H. And if you want the answer for CE, it will roll about D. So now I got to adjust my numbers because my rolling radiuses were measured from E. From E. Delta J is to how far he is out. Delta J is out 8 feet. I went astray when I erased this cut line here and moved it over to this other side. I'm still not happy with that cut line. If you're going to shorten this member, it's going to roll, that ought to go right through point G for the rolling of this piece of plywood relative to this piece of plywood. Delta J is to how far he is from the rolling radius point, 8 feet, as how far this goes down is to how far out he is. Something fishy here. How far out is this guy here? Dang. 10 feet. as how far is this guy out on this piece of plywood? 8 feet. And therefore, this downward motion is going to be 4.25? 1.25. I was going to say, it sounds a little big. Delta J, thank you, is 1.25. And it is feet. It rolls dimension feet. Now here's what your pieces of plywood look like. They come across here like this. That piece is there just because you held it with your hand. Then you cut this piece out, and let me show you the deflection. Goes down. And it's your job now to bring this guy up 1.25 back to 0. That means this one will raise up 1.25 and it'll put it to 0, and I'm going to plot the influence line through 0. Zero. Now then, if this point moved back up 1.25, how far did this point move up? It's rolling about point B now. Here's your structure. Sadly, this pin doesn't fit the roller. You moved it up 1.25. Then how far did this point move up? All right, it only moved up half as much, right? No, not half as much, I'm sorry. It moved up 1, 2, 3, 1, 2, 3 fourths of this number here. In other words, whatever this moves up, being out here 8, 8, 8, 8, this point's going to roll about point B to get this back on here. 1, 2, 3 times 8. In other words, 3/4 of this number. How much is that? 0.938. Then I'm going to plot right here, 0.938. What does the rest of the structure look like? Straight lines. That's all you got to know. In other words, you find one point that's 0 because that's easy to get. You find out where one of the other points go, and then the whole thing will just arc up as like a rigid body. And therefore, I can tell you if this is 0.938, I can tell you what these ordinates are. And I can tell you what that ordinate right here is. How big is that one? 0.938. Now the proof will be in the pudding. I'm assuming that the influence line really does look like that. If you want to see if it really works or not, here's how we can do it. We'll take the original structure. That's how come I got so many of these, I remember now. And we will put a unit load at what point? The answer is any point. Pick a point. If you put the unit load right here, what should you get for the answer? 0.31 something, because it's a third of the way out. Put the unit load here, you ought to get 0.6 something something. Put the load right there, you ought to get 0.938. I won't swear we will, because I've only made 15 mistakes getting here. So, but let's put the unit load at G. we are looking for the force in member FH. There's how I'm going to cut member FH, right there. I'm going to seriously cheat, and I'm going to go ahead and show the forces right on this rather than redraw this as a free body. This will be GI, this will be GH, and this will be FH, which is the guy we're looking for. You want FH? Yeah. Who do you hate? I hate these two. I'm going to sum moments about this point right here. Putting the 1 here causes, I'll leave this for you, 0. 0.25 here, and causes 0.75 here. Here's your free body. Some moments about point G is equal to 0 is equal to minus 0.25 times his moment arm, 3 times 8, plus FH times his moment arm, 10, and who knows. If it doesn't come out, I'll get it fixed before I come to class. 0.6? Well, that's a sad shame. Because it's supposed to have been 0.9. You sure you don't have a...
On the other problem,
On this one?
it got 0.9, whatever.
Yeah.
I thought that it was half of the 1.25, not 3/4.
Rolling about point B should go up 3/4. But all right, it happens. I'll find it. I won't tolerate it on a quiz, but I'll find it on mine. I don't see it right offhand, just quickly either. Delta J is to how far he... Phooey, here it is right here. Which way is delta J? Vertical. How far is he out to find the vertical? 8. Why didn't you tell me that before?
You kept changing it from 8 to 10.
No, don't give me the 16, man. I can't stand any more mistakes. As 1 is to how far he is, the rolling radius from G. What is this number? How big?
0.8.
0.8. What is 0.8 times? It works out? See there? Class is over. Somebody stick around. Let me at least write the numbers down right here. Oh, this is FH, huh? Okay. Thought you said this was 0.6.
That answer? Yeah, 0.6.
So that's... Okay, so this was 0.8 of a foot. Yeah, I see. So I got to still go find this thing here. That's right. He's right. So this one rolls up 3/4 of 0.8. And you said this one turned out?
Yeah.
Good.
All right. There we go.
Got to be careful. This stuff here? Well, I think everything through the end of the book is on the quiz, isn't it?
On this next.
Yeah, I think so. I think it's what the syllabus says. Yeah, you're supposed